or this one can be expressed by this minus nu. And or Ij equal to lambda. Or otherwise this one can be expressed by this. I simply try to make the whole thing complete. So for the plane stress, we can have is this. For the plane stress province, for example, we say 3,3 equal to 1,3 equal to 2,3 equal to 0. Okay, so for example, we work on this one. So how about this? Let me continue to implement this one here. So for example, for this case, the tau 1, 1, for example, for taking this equation, tau 1, 1 is equal to, say, E, and tau 1, 1 minus nu E, tau 2, 2 plus tau 3, 3. Okay. If I take this equation and I simply implement the three terms here, 2, 2, and 3, 3, okay. So in this case, then we pick up this one. So do you want certain symbols? Say, let me give some. So this is equation 1. And the 2 are equation 2. And this one, let me call the equation 3. Okay. So using those equations, then using equation 3, we simply have the 3 zero stress component introduced to equation 3. Then we have is 1, 1 equal to E, and tau 1, 1 minus nu, tau 2, 2, and epsilon 2, 2 equal to E, and 2, 2 minus nu, 1, 1. Okay. Then 3, 3. The 3, 3 with that information should be equal to this one. Okay, and then for string, again using equation 1, then that can be easily obtained. It simply is 2G tau 1, 2. That's it. So for this equation, again, the right-hand side are non-zero stress element 1, 1, 2, 2, tau 1, 2. Okay, on the right-hand side, that are the non-zero stress elements. And after introducing the zero elements here, on the right-hand side, in particular, I'd like you to pay attention to here, about this term. Again, for plane stress, and the model, material model is something like this. The planes, the thin film, or metal sheet, okay? So for example, this is the one directions, and this is the two directions, this is the three directions. And we said in the three directions, the stress pretty much is zero. However, the strain in Z direction is not zero. The strain in the three direction is given by this. In general, it's supposed not to be zero. Okay, that is an important concept to this one. Okay. So right now we have this, and you can do the inverse algebra and to describe an equivalent expression. Right now I want to have, for example, the stress on the left-hand side. So that can be like this, tau 1, 1 equal to something, and tau 2, 2 equal to something, and tau 1, 2 equal to something in terms of the strain. Again, you simply perform the simple algebra, and here is the result. And that one equal to E, 1 minus mu square, and epsilon 1, 1 plus mu epsilon 2, 2. This one equal to E, 1 minus mu square. Okay, something like this one. And that's it. Okay. And now for the plane strain. For the plane strain, and let me take this 1, 3, 2, 3. 3 is equal to 0. Let me take the zero elements like this. And again, and for these equations, let me write up a few terms. Will be easier for our later one. So say for this equation, let me write up the tau 1, 1. And let me expanding, for example, using engineering notation, that'll be a little bit more intuitive for everyone here. So this one will be equal to E, 1 plus mu, 1 plus 1 minus 2 nu. Minus mu, epsilon 1, 1 plus mu. Epsilon 2, 2 plus 3, 3. Okay, and tau 2, 2 will be in the similar patterns, and that's a 2, 2, 1, 1, 3, 3, and 3, 3 will be similar patterns. Okay, so with this one, ready, let me call this is equation 4. Okay, so here let me utilize equation 4. For equation 4, we simply plug in the 0 element of the strength there. So let me start with this one. So tau 33 equal to from this point onward, how it depends on my algebra. Then again, here I using equation 3 for the strength. I simply want to express in terms of stress, and after the few steps of the operation, this will be this one. Okay. Then tau 22 will be equal to, again, knock out the tau, knock out this one, and what is the best way to do this one? Let me rewrite this one. Tau 33 equal to nu tau 11 plus q2. Okay, and here if allow me to using elastic notation for nu, basically that is also equal to lambda q, lambda plus mu, and 11 plus q2. Okay, either way, here I just simply replace the definition of nu by non-constant here. Okay. And since for stress, if we write in terms of non-constant, that has less writing. We don't need to write that much. Okay, so in this way, let me use changing notation, tau 22. Again, for example, using this notation, tau 22 simply is equal to, for example, lambda epsilon 11 plus 22 plus 33. And plus 2 mu lambda 2 2. Okay, so in this way, when tau 22, when the element equal to 0, then tau 22 simply is equal to lambda plus 1 1 2 2 plus 2 mu. Okay. In a similar way, tau 11 equal to okay. So therefore, from here we can write everything here. Tau 11, tau 22, tau 33 simply equal to whatever in terms of the strength. Okay, and here calculation for this, for this, for this. Can I leave that to you? Tau 33 equal to the function of those things. Tau 33 equal to the function of tau 11, tau 22. Then you further describe, you further introduce tau 11, tau 22 into here, then you can have the expression here. But I do have an equivalent expression in terms of the engineering notations. Let me copy that one here. 1 plus mu, 1 minus 2 mu. One minus mu, 1 minus mu, 1 minus 2 mu. Okay, I think that is what I need here. Again, on the other side, we can also have strain compared to stress. So compared to strain to stress, epsilon 11 equal to 1 plus mu E. There's a long writing here. Okay, that's it. So for each plane stress, plane strain problem, I have given you the strain related to stress, vice versa. Strain related to stress, or vice versa. Okay, so we have it either way. And the final thing is, I want to make a note to you is how to convert if you have the template for plane stress problems, you want to convert right away from the template of plane stress into plane strain. Okay, so again, for example, if you have a cheat sheet, for certain reasons, you only write down this formula for plane stress without this portion available. I want to let you know how you, based upon this one, to extend and to obtain the result here. So we can do this one. For the plane stress, for example, and let me take one element, say epsilon 11 equal to E, and tau 11 minus nu E tau 22. Okay. For plane strain problems, we have epsilon 11, and let me define this is E start, tau 11 minus mu start, and E start, tau 22. Right now you can see I used the start notation, but right now the two forms are at the same template, right? Basically here I utilize the template for plane stress to describe the plane strain. So as long as we are able to find out the expression of the start in terms of this one, so compared to this one. Right now I'm going to compare the two equations. From here you can see basically E start will be equivalent to this one. So therefore you can see the E start simply equal to E 1 minus nu square. And then also compare to nu, and nu start divided by E start equal to E and nu 1 plus nu. So from here you can determine the nu start equal to nu 1 minus nu. So that's it. This tells us a good properties is such that, for example, we can utilize the plane stress as a template to write down the plane strain equations. As long as in the plane strain equations you replace the corresponding Young's modulus by this number. Got it? Okay? And or vice versa. But here I give you one way should be good enough. And again, replace in this way you replace the nu by this number, then everything, this expression in terms of the template of plane stress will be exactly the one like this one here. Okay. In this one have a good way. So many times when people doing the analytical research, they usually be lazy like me. I only do say, oh, that is a plane stress problem. But for if the model has the very huge Z dimensions, then the problem can be right away available to plane strains by simply replacing the parameter like this one. That is shown in the papers here. Okay. Good. And this one basically marks the big chapters of Hooke's law, stress-strain relations. So Mark, we can finish this